Zeal Education Society, redefining excellence.
Welcome back. In the previous two lectures, we have seen jury stability test for the stability analysis of digital control systems. In today's class, we will see the bilinear transformation combined with Routh stability test for the analysis of stability of digital control systems. Now, let us make some remark like about Routh stability test. And you are well familiar with the Routh stability test. Routh stability test, which is also called as Routh-Hurwitz test, is applicable to the systems represented using transfer function in S-plane. And the stability conditions in S-plane is that all poles must be in the left half of S-plane, then the system is stable. If any of the pole is in the right half of S-plane or repeated poles are on the imaginary axis, then system is unstable. And if non-repeated poles are on the imaginary axis with remaining poles in the left half of S-plane, then the system is marginally stable. So if this is the S-plane with the conditions of stability, then the Routh stability test can be applied. Now this Routh stability test then will also be applicable to all such planes having same stability criterion. Let us make a mark, or I will write it here. It is also applicable to complex planes like S-plane having same stability conditions as that are applicable to S-plane. And that means if we can transform the characteristic equation P of Z equal to 0 to that new complex plane, then we can apply the Routh stability test to this system also. So what shall be the characteristic of this transformation? That means if we can transform Z plane to a new complex plane such that number one, the inner part of unit circle is transformed to left half of new complex plane. Second, the imaginary or the circumference, I will say, circumference of unit circle in Z plane is transformed to imaginary axis of new complex plane. And you may feel that this is S-plane, the new plane is S-plane. Yes, it may be S-plane, but the plane we will get here is different than S-plane. And the outer part of unit circle in Z plane is transformed to right half of new complex plane. So if these three conditions are satisfied, then such transformation that we are going to use is called as bilinear transformation. And the plane which satisfies this condition is W plane. So let me mark it. W plane satisfies above three conditions, and the bilinear transformation between Z plane and W plane is Z is equal to 1 plus W upon 1 minus W, or W is equal to Z minus 1 upon Z plus 1. So let us check whether this is valid or not. Now let us consider only the real part, because if we consider a left half of S plane, means left half of S plane has real part less than 0. Imaginary axis has real part equal to 0, and right half has imaginary part, real part equal to greater than 0. So here, if I put Z which is less than 1, so if Z is less than 1, this part becomes negative, this is positive, so overall this becomes negative. So W becomes negative, or real part of W becomes negative, means it is the left half of the W plane. Now if I put Z equal to 1, that is circumference, then 1 minus 1 is 0, then the real part of W is 0, that is imaginary axis in W plane. And if I put Z greater than 1, so both the numerator and denominator of W will be positive, and real part of W becomes greater than 0. Correct? And that means these three conditions are satisfied with this bilinear transformation, and W is that new plane. So let us mark it. Let we have the Z plane. This is the unity circle in the Z plane. And then let me mark the W plane. Real, imaginary. Even here there is real and imaginary, because both are complex planes. And then if I try to transform, this inner part will be transformed to left half, this outer part will be transformed to right half, and this what I can say, circumference will be transformed to imaginary axis, and this is the W. So now what we can do, if we transform the characteristic equation P of Z equal to 0 to W plane, then we can apply Routh stability test. So let me mark the steps in stability test. The steps are: number 1, transform P of Z equal to 0 to P of W to 0 by the bilinear transformation Z is equal to 1 plus W upon 1 minus W. And second is apply Routh stability test. Very simple. Routh stability test to what? To the characteristic equation P of W equal to 0. So what we have seen so far, let us revise quickly that Routh stability test can be applied to S-plane. It is also applicable to a similar plane which has same stability conditions. And that means to analyze the stability of discrete time system, we can use Routh stability test if we can transform the characteristic equation P of Z equal to 0 to a new characteristic equation in new complex plane. And how that complex plane shall be? After applying the bilinear transformation, the inner part of unit circle in the Z plane shall be transformed to left half of W plane or the new plane. Outer part of unit circle in Z plane shall be transformed to the right half of new plane, and circumference of unit circle in Z plane shall be transformed to imaginary axis in the new plane, and that new plane is W plane. And the bilinear transformation is Z is equal to 1 plus W upon 1 minus W, or equivalently W is equal to Z minus 1 upon Z plus 1. So to consider the concept, let us solve one numerical example. Investigate the stability of system with characteristic equation P of Z is equal to Z cube plus 2.1 Z square plus 1.44 Z plus 0.32 equal to 0. This example was considered in Routh stability test and the outcome was system is stable. So let us verify, are we getting the same or not. So here I will mark that using bilinear transformation and Routh stability test. Now let us start solving. So what we have the characteristic equation in Z plane, that is P of Z equal to Z cube plus 2.1 Z square plus 1.44 Z plus 0.32 equal to 0. So the step number 1 is P of W. Obtain P of W. So P of W will be equal to what? Replace every Z with 1 plus W upon 1 minus W. So it will be 1 plus W upon 1 minus W whole cube plus 2.1 into 1 plus W upon 1 minus W, this is the equivalent for Z, so square, plus 1.44 1 plus W upon 1 minus W plus 0.32 equal to 0. Now I have to expand this, and if we expand this will be 1 plus W cube upon 1 minus W cube. Here I am getting 1 minus W square, here I am getting 1 minus W, and here there is no term in the denominator. So after taking LCM, we will get the term 1 minus w whole cube in the denominator. And so P of w will be equal to 1 minus w whole cube. So this will be 1 plus w whole cube plus 2.1 into 1 plus w whole square into 1 minus w, because we are taking LCM. Now the denominator is common, 1 minus w cube. Here the term was 1 minus w square. So additional 1 minus w will come here. Same way here, 1.44 into 1 plus w into 1 minus w whole square plus 0.32 into 1 minus w whole cube, and that will be equal to 0. So let us expand this. So 1 plus w cube is w cube plus 3w square plus 3w plus 1 plus 2.1 in the bracket. I will write this as 1 plus w square is w square plus 2w plus 1 whole multiplied with 1 minus w plus 1.44 into 1 plus w into square of this will be what? W square minus 2w plus 1 and plus 0.32 into bracket 1 minus w cube is 1 minus 3w plus 3w square minus w cube, and this will be equal to 0. So calculations are tedious, but we have to do it. So this will be equal to w cube plus 3w square plus 3w plus 1, and this will vanish with this, that is why it is written here 0, plus 2.1 in the bracket, this will be minus w cube plus w square minus 2w square, so it's minus w square plus 2w minus w, so it's plus w and plus 1 plus 1.44 in the bracket, this will be w cube minus 2w square plus w square, so it's minus w square. Then this will be plus w minus 2w is minus w plus 1, and this will be I will make it directly. So let us keep this as 0.32 into bracket 1 minus 3w plus 3w square minus w cube, and this is equal to 0. And now let us collect the terms. So w cube in the bracket, this is 1 minus 2.1 plus 1.44, and this will be minus 0.32 plus w square in the bracket, this is 3 minus 2.1 minus 1.44 and plus 0.3296, so 0.96 plus w in the bracket 3 plus 2.1 minus 1.44 minus 0.96. Now plus constants, I will correct the constants. So it's 1 plus 2.1 plus 1.44 plus 0.32, and this is equal to 0. So let us do the calculations. 1 minus 2.1 plus 1.44 minus 0.32, so it is 0.02 w cube plus 3 minus 2.1 minus 1.44 plus 0.96, that is 0.42 W square, plus 3 plus 2.1 minus 1.44 minus 0.96, that is 2.7 W, plus 1 plus 2.1 plus 1.44 plus 0.32, that is 4.86. So we have got the P of W, and now in P of W, all powers of W coefficients are present for all powers of W. Also, all coefficients have same sign, so necessary condition of the Routh stability test is satisfied. Now let us form the Routh array. So then the Routh array is, I will get here W cube, coefficients of this will have this element and this element, 0.02. I presume that you know Routh stability test, you have learned it earlier. Then 2.7, elements in the row W square will be 0.42 and 4.86. Elements in W raised to 1, this multiplied by this minus this multiplied by this divided by this. Let us do it. 0.42 into 2.7 minus 4.86 into 0.02 divided by 0.42. So it is coming 2.4686. 2.4686, and then W raised to 0 will be this multiplied by this divided by this will be 4.86. And now I have the conclusion. So as there is no sign change in the first column of Routh array, the system is stable. Done. No doubt, Routh stability test has very less computations as compared to the jury stability test, and this is the advantage. However, this computation is complex. So if you can compute this very correctly, then the rest part is very simple. Step number 2. And if the order goes beyond 3, it becomes very difficult for the expansion. So this method is suitable only up to third order systems. If you go beyond that, then the calculations become very difficult. So even in the next class we are going to solve more examples on this. We will consider again third order system only. We will not go for the fourth order system. If there is fourth order system, jury stability test is preferable. It is enough in this class. Let us meet again in the next class. Thank you.